magnetic field of a semicircular wire. Let's say the current is flowing like this. And we want to find the B field in the center. And then we can do also off center. So the center is actually going to be pretty easy. So if you have a like this, so then you do dB is mu 0 I over 4 pi dl crossed into r hat over r squared. So you take a little piece and the dl is like that, right? Then the r hat is the unit vector pointing to where you're trying to find the B field. So then dB, so then you have, remember the mu 0, well, let's just leave it like this. And then dl is going to be magnitude dl, magnitude r hat, times sine of the angle over the r squared. So if you're doing it at the center, then the radius is just simply going to be constant. So it's just going to equal to the radius of the circle. And then the magnitude of r hat is 1. The angle between the dl and the r hat is going to be 90 if you're right at the center. So that angle is just going to be 90. So that's going to be 1. And then when you integrate this, then it's going to be just, well, you don't actually even need to integrate anything because the radius is constant. You can pull it out of the integral. And you have mu 0 I over 4 pi r squared and an integral dl. Right? So since the radius is constant, we pulled it out of the integral. And then the integral dl is going to be the circumference of a semicircle, right? So then it's just pi r. Pi r, right? And then that's going to be cancel that, and then r and the r cancels. So you have mu 0 I over 4r. Okay? So the magnetic field at the center of a semicircle is mu 0 I over 4r. Now, if you make it a complete circle, remember the magnetic field is into the board, right? So then if I add the second half of the circle, the magnetic field just doubles. You have dl crossed into r hat. So then you still have dl crossed into r hat into the board. So it's not like electric field. For electric field, if I have a semicircular rod, the electric field there is to the right. If I have another semicircular rod, the electrical field of that is to the left. And if I have a complete circle, the electric field is 0 inside. But for magnetic field, the magnetic field is into the board, and then the right side, it's also into the board. So you double it. So for the magnetic field of a circle, this just doubles. Mu 0 I over 2r. And now if I make it n number of turns, then it becomes n mu 0 I over 2r. This is called the coil, magnetic field of a coil. N mu 0 I over 2r. So the proof is pretty easy. That's it. Just that application of Biot-Savart law. Magnetic field at center of loop. See, that's kind of what the magnetic field looks like at the center of a loop, you see. So we're deriving the equation for right at the center, right there in the middle, you see. And the equation, you see they're doing the Biot-Savart law, mu 0 I over 4 pi r squared. Then you get mu 0 I over 2r, you see. And then mu 0 is 4 pi times 10 to the minus 7. So that's it. And then if you have n number of turns, then you do n mu 0 I over 2r. Okay. But now, what if I wanted to calculate the magnetic field a little bit off center, like somewhere here or somewhere here? Is that going to be stronger than at the center? Let's see here. What if you look at the picture? What do you guys think from the picture? Do you think the B field here is stronger than, let's say, here or here or here or here or here? Or is the field here stronger than here? So the way to determine that from the picture is to see where the B field is more concentrated. Is it more concentrated here than here? It seems like from the picture you can't really tell. Anyone, what do you think? Just looking at that picture, or is the picture not good enough? Let's see here. What if we do? This is something else. That's a solenoid. So we'll do a solenoid later. We're doing a coil now. This is kind of a nice view. You see here? The B field of the coil. You see, so do you think it's stronger here towards the end or at the center? See, they used iron fillings here to actually do this. So the way that you can actually do this, you could wrap a copper wire, and maybe they have a plate here that it goes through the hole of the plate. It comes below the plate. Oh, that's kind of what they did, I think, here to illustrate this. So you see, they took a plate, they drilled a hole in it. You see that hole? And they took copper wire, they went inside and out, and now they connected this to a battery. And then on top of the plate, they put iron fillings. And you see the iron fillings line up with the magnetic field, you see? So what do you think? Is it stronger towards the edges or the stronger near the center? Who says center? Anyone? Daniel? Anybody for center or edges? Daniel says, sure, why not? Just why not? Or does it look more concentrated here? Yeah? Edges look darker. So I think the edges. You're right. It's not that clear whether the edges are. Yeah, it's not that clear, but I think the center looks stronger because the center looks more straighter. Usually wherever it's more straight, that tends to mean it's stronger. Where it starts diverging, it means weaker. You see? Okay, so let's see here. Okay, so let's. So how would we do that? Okay, so now let's learn how to do the magnetic field. Let's say we could do this with numbers much easier. So let's say the radius was, let's say was 1 meter. So let's say half a meter this way. What would be the magnetic field? So if we learn how to do it half a meter this way and half a meter inside, Then basically a coil, if we want to know halfway this way, it'll be a combination of the magnetic field half a meter out and a half a meter in. Then we'll add those out and in and see what we get. So let's do it with numbers. What would be the magnetic field of a complete coil? Let's do the right at the center first. Let's say, make it easy. The radius is 1 meter. The current is 1 amp. And let's say there's only one turn. So according to this equation, the magnetic field at the center, well, according to this equation, it would just be, so the N will disappear. So you just have mu 0 times 1 over 2 times 1, right? That's it. So if you just have, basically this is canceled. So mu 0 over 2. And mu 0 is 4 pi times 10 to the minus 7. So a magnetic field at the center of a circle will be 2 pi times 10 to the minus 7 Teslas. Okay, then we can compare our answers to that for this case. So then half a meter out, what would we do? So let's draw that a little bit bigger. So you have DL, and then we have R hat is facing this way towards that. Okay, then we're gonna have here, this is 1 meter, this is a half a meter, and this is gonna be, so dB is gonna be mu 0 I over 4 pi. Then we're gonna have here DL, magnitude of R hat times sine of theta, where that's the theta here, right? Between the DL and this one here, sine of theta over the R squared, and this is the R squared. Okay, so let's see here. Okay, this kind of resembles when we did the voltage, right? So we could look at this triangle. So we could say this is a half, this is 1, this is the DL vector, and this is the R hat vector. You see, this is 90 right here. So basically this theta that we're referring to is this theta. So you know what, let me call this alpha, because usually we call this theta for the semicircles, right? We call this guy theta. So this one alpha, I'm going to call this guy, the angle between the DL and the R hat vector. You see? So this one I can call 180 minus theta, and this is R. Right, so then what's going to happen? R squared is going to equal 1 squared plus 0.5 squared minus 2 times 1 times what? 2 times 1 times 0.5 times cosine of 180 minus theta. Law of cosines again. All right, so then you're going to have here R squared is going to equal 1 plus 0.25 minus 2 times 0.5, so that's just 1. Cosine of 180 minus theta is negative cosine theta, right? Negative cosine theta, so this becomes positive cosine theta. Okay, but now how do we bring in this sine of alpha? That's sine of alpha, but then this angle here, because the whole thing is 90, right? DL, The reason why it's 90 is because DL is a vector along the current direction, right? And then the current is tangential to the radius vector. So that's why that angle is 90. So we can say this angle right here is 90 minus theta, right? 90 minus alpha, I meant. 90 minus alpha. So how could I bring that in? Sine of alpha. Can't I say sine of alpha is going to be sine of alpha is going to be cosine of 90 minus 6.5 squared is equal to cosine of that. Where am I stuck? 90 minus alpha. Let's see. If I say, what if I use law of sines? Sine of 180 minus theta over r is equal to sine of 90 minus alpha over 0.5. Right, so sine of this over this is equal to sine of that over that, over the 0.5. Okay, then what's sine of 180 minus theta? I believe that's the same thing as sine theta, right? Sine theta over r. And then this one, sine of 90 minus alpha, is going to be cosine alpha. Over 0.5. Sine of 90 minus alpha is cosine of alpha. This might be a dead end. Let me see if that's going to help. It seems like it went into a dead end because I'm trying to find a relationship for sine of alpha. So I already have a relationship of r squared in terms of theta, right? So I'm trying to get sine of alpha to relate to theta. So this probably went to a dead end. Okay, let's see. I think that was a dead end, but we'll keep that in there just in case. I won't completely erase it. So let's do it this way. Let's use law of cosines for this part. So then let's say 0.5 squared, back to law of cosines. So 0.5 squared is equal to r squared plus 1 squared minus 2 times r times 1 times cosine of 90 minus alpha. All right, so then I'm applying the law of cosines. In other words, here I applied the law of cosines where I made this the c, and then this A and this B, and then this is the angle. And then I got this out of that. And now I'm applying the law of cosines to this. This is the C. This squared is this squared plus this squared, right? Minus 2 times R, 2 times R times 1 times cosine of that angle, that small angle. Okay, that might be more fruitful. Why? Because we have here 0.5 squared is R squared plus 1 minus 2R. And then what's cosine of 90 minus alpha? Sine of alpha, right? Yeah, sine of alpha, which I see a sine of alpha here. Aha. Sine of alpha. There you go. Let's see what we could do with that. So now how could I get rid of sine of alpha? I can bring this to this side. 2R sine alpha equals to R squared plus 1 minus 0.5 squared. So 2R sine alpha, right? 2R sine alpha is equal to R squared plus 1 minus 0.5 squared. And then sine of alpha would equal 1 over 2R, R squared plus 1 minus 0.25. One minus 0.25, 0.75. Right? But then here we have an expression for R squared also. So it's almost like you're applying the law of cosines twice. One making this the C, right? And then one making this the C. Okay. And let's see here. Then we have R squared. From here we have R squared is 1.25 plus cosine theta, right? And can we substitute that there? Let's see here, sine of alpha, 1 over 2R, then R squared is going to be 1.25 plus cosine theta plus 0.75. Sine of alpha, 2R, what is that? 2 plus cosine theta. So how does this help us at all? Or does it not? Well, if we go back to the original integral, right, then we're going to have what? dB is going to equal mu 0 I over 4 pi. This is going to be your dx, right? And then r hat, sine of alpha, which is going to be this guy. So I can substitute sine of alpha is this one, right? Oops, I'm trying to capture everything. So sine of alpha is this one. So whatever the sine of alpha is, replace it. 1 over what? 2r, 2 plus cosine theta, right? For the sine of alpha. And then you got the r squared is equal to what? So this is the sine of alpha, and then the r squared is going to be the 1.25 plus cosine theta. 1.25 plus cosine theta. Right? That's the r squared down here. Are we stuck still? Oh, okay. Remember what dx is here, the dl. It's the same thing that we had before for the rod. Dx is equal to, if you go like this, The x is a length along the circle, and then we got dx is equal to r d theta. And then this is the radius, right? So dx is r d theta. So we have here dx is equal to r d theta. Okay, we should be able to actually integrate that, right? So let's see here, dB is equal to mu 0 I over 4 pi r integral. Okay, so then you're going to have here on the top, we have 2 plus cosine theta, then d theta, right? And then on the bottom, we have 1 plus 2.5 plus cosine theta. Then we have what, 2? Oh, that 2 can come out 2, right? The 2 can come out. And then what's r? R is equal to just square root of this. Oh, so basically this becomes 3/2 power, right? Becomes square root of this, the r. So you have a square root, so that makes it 3/2 power. Okay, and then the integral, the limits of the integral are from 0 to pi over 2, and then you can double it. 0 to pi over 2. So 0 to pi over 2. Oh, and then double it. And then that should cancel the 2 down here. Wow, nice. So you have to kind of apply 2 law of cosines twice. Okay, so then the r cancels, the 2 cancels the 2. And you have here the radius of the circle was 1 meter, right? So that one's gone, 1 meter. So you have b is equal to mu 0 I over 4 pi. That one's gone. The 2's cancel because we doubled it, plus whatever the integral gives you. Okay, so let's go to integral. 2 plus so we have here 2 plus cosine x, right? And then on the bottom, 1.25 plus cosine x. So 2 plus cosine x over 1.25 plus cosine x, right? 2 plus cosine x, so 1.5 plus cosine x to the 1.5 power. And now 0 to pi over 2. Okay. It should be in radian mode already. So I believe the website already does it in radian mode. Oh no, my most hated website, my arch enemy, the enemy of learning and progress, Chegg. Okay, 1.6377868. Okay. So what is that going to be? Well, remember what the magnetic field of the whole circle was at the center. So let's use that. It was 2 pi times 10 to the minus 7. So that's 6.28 times 10 to the minus 7 for the complete circle at the centers. 6.28. So then what is mine here? This is going to be, well, mu 0 is 4 pi times 10 to the minus 7. The current was 1 amp over 4 pi. Also, that one cancels. So it's just 1.6377868 times 10 to the minus 7. Compare that to the complete circle at the center is 6.28. So I'm way, way less than that. 6.28 versus 1.63. But I haven't completed the process, right? I only did semicircle half a meter out. So now I'm gonna do a semicircle half a meter in. So what changes in the integral? Half a meter this way, right? Then your integral looks like this. Probably a couple things change, but a lot of things probably stay the same. Let's see here. So let's draw that so we can be, it's probably a couple signs that change from plus to minus. So if you're a half a meter in, so now this is your DL. This is your, now you're over here. So this is your R hat vector. Then you got here is R. And then this is the triangle. This is 1 meter here. This is 0.5. And this is the little r. And then now this is the, when you do the alpha, this is the alpha. Okay, so what changes here? dB is equal to mu 0 I over 4 pi. So I'm just going to kind of start it fresh. Let's see what changes, and then we can compare it to that one. So mu 0 I over 4 pi, let's see, dl, magnitude of r hat, sine of alpha, which is this one. Then you have here over r squared, and then r squared is this one. So then I'm going to do, this is theta. So then I'm going to apply the law of cosines to this. R squared is equal to 0.5 squared plus 1 squared minus 2 times 0.5 times 1 times cosine of theta. Oh, so the difference is that it's not 180 minus theta. Yeah, it's not 180 minus theta. So then it stays as a negative here. Okay, so then you have here r squared is equal to, this is 1.25 minus cosine theta. So then instead of r squared is 1.25 plus cosine theta, it's minus cosine theta. That's one of the other differences. But now let's apply the law of cosines again with this guy as the C. Okay, so then 0.5 squared is equal to this squared, right, plus this squared minus 2 times r times 1 times cosine of that. And then what is that? If the whole thing is alpha, oh, that would be alpha minus 90 degrees, right? This one will be alpha minus 90. Oh, so instead of alpha 90 minus alpha, it's alpha minus 90, because alpha is an obtuse angle, right? Alpha is an obtuse angle, so it becomes alpha minus 90. So instead of 90 minus alpha, it's alpha minus 90. So then let's see how that changes. Alpha minus 90. And then let's see here, 0.5 squared is equal to, well, let's just write it as 0.25 r squared plus 1 minus 2r. Oh, then this is going to be cosine of alpha minus 90 is negative sine of alpha. Oh, yeah, then that switches to positive sine of alpha. Ah, okay. So it becomes kind of like this one, except that one also switches signs. So in other words, this one switches signs, and that one switches signs to positive, right? So it becomes positive 2r sine alpha. So now when I'm solving for sine alpha, so then it's going to be 0.25 sine minus 1. Okay, so then it's going to be negative 0.75 minus r squared over 2r. Well, so then it's just basically, you could factor out the negative and just have a negative there. Okay, so then let's see what happens to the integral. dB is equal to mu 0 I over 4 pi. dl is going to be r d theta again. And then sine of alpha is going to be, I could put the negative outside, 0.75 plus r squared over 2r, right? And then you're going to have r squared. It's going to be 1.25 minus cosine theta. Okay, then I'm going to go 0 to pi over 2 and then double it again. So the 2 is going to come out. I'm going to double it. So that's going to cancel. And then the r is 1 again. And then this r is going to be another 1/2 power. So a lot of the things are the same, 3/2. So then what's the final result? How is the integral different? Oh, the top changed quite a bit. Before it was 2 plus cosine theta. Here, oh wait, I forgot to put the r squared. Let's put the r squared. What is the r squared here? R squared is 1.25 minus cosine theta. So negative mu 0 I over 4 pi, 0 to pi over 2 d theta. So if you put r squared is 1.25, you're going to get what? 2 minus cosine theta over 1.25 minus cosine theta to the 1.5 power. Let's see, is that? Oh, okay. So in essence, then that's it. So you just ended up getting 2 minus cosine theta. Here it was 2 plus cosine theta. And then 1.25 plus cosine theta, and that's also minus. Oh, then that's easy to remember. If we go inside, so you just basically, this is one of those things where you do it once, and then you say, okay, I got the pattern. I don't have to keep doing it. All I know is that as when you go inside, it changes to minus and minus. But the numbers are the same. Okay, cool. Okay, so then let's do that integral. Let's see what's going to happen. What should happen? Should this magnetic field be stronger or weaker than the other half of the circle? If I go half a meter out, I'm further away from the semicircle, right? Yeah, it should weaken. But if I go half a meter in, the magnetic field there should strengthen. So that's what my question is when you make a complete circle, if you go to the sides, you're farther away from this half of the circle, but you're closer to this half of the circle. So who wins there? What's the total come out? Daniel says the total is going to come out weaker than the center still. So let's see if he's true. We're doing this just for you, Daniel. See how important you are? So 2 minus cosine theta, 1.25 minus Daniel says, gee, thanks. I like that. Yeah, well, you see how important you are? We're doing it just to disprove you. I didn't say the second half of the sentence. Oh, it's taking a while. Oh, wait. Hold on. No answer, it says. Why? Use parentheses. No answer. Your calculation was aborted because it took too long. Okay, let's see here. Let's go to mode, go to radian mode. Okay. So 2 minus 1. 2 minus cosine of x divided by you're going to have 1.25 minus cosine x. Right, to the power 1.5. And then you put the variable x, and you put the variable 0, and then pi over 2. Okay, come on, come on. See, it says busy here. Oh, gave us an answer. You see? And you can kind of see if you put it in right. 2 minus cosine x, 1.25. So where's the focus? You see? Nice. 2 minus cosine x, 1.25 minus cosine x. Yeah? It had an answer. 6.188678. Six point one eight eight 8678. So 6.188678. And then this is already okay. Forget the negative here. And this is 4 pi times 10 to the minus 7. So the 4 pi cancels, and current is 1 amp. So it's literally B for this semicircle, half a meter in, it's B 6.188678. Oh, but now let's add that to the semicircle like this, half a meter out. Well, what did we get for that? So, it's gonna be close. B for the 2 semicircles. Okay, the other one we got 1.637786. Adam. Oh, yay, yay, yay. Plus 1.637786. 7.826465 times 10 to the minus 7. Okay, what was it at the center? What was it at the center? Okay, at the center it was just mu 0 I over 2 pi r, no, over 2r, right? So it was just 4 pi times 10 to the minus 7 times 1 over 1 times 2. Yeah, it was 2 pi. Oh, yeah. 6.28 something something times 10 to the minus 7. So it's stronger as you go towards the edges. It's stronger as you go towards the edges. So Daniel, is that what you had said? It's stronger towards the edges or the center? Oh, you said it's stronger at the center. Yeah. You know what? I don't blame you. That one wasn't clear. At least from the pictures, you can't really tell, okay, if it's more concentrated. It does look very concentrated here. And here it looks more loopy, you know. But that's probably our eye is focusing on over here, you know, over here, but not necessarily right there. The calculations are telling us like right there, the B field is stronger than right there, you see, but not necessarily here. Here it might be weaker than here, you see? You see, Daniel? So that's why your eye is going to here and it's saying, oh, you see the field is diverging quicker here. So I would agree that the field here is probably weaker than here, but the field here is stronger than here. You see, so as you go that way and that way, the field gets stronger. You see how the iron is wrapped very tightly as you get there. They're feeling the effect of that strong field. But of course, when you get here, yeah, then it's diverging. You see, of course, outside is very weak. The field outside. We could even probably calculate that if we wanted to, but that takes a long time. We could do the integration to calculate the field on this side. On this side. Then we would have to do this semicircle over there. And then we would have to do this semicircle behind it. See, if we were in class, I might have given that as an extra credit on the test. That would be an extra credit. And say this semicircle, you can do the field there because we already learned how to do that, but then we haven't learned how to do behind it. But you could set it up still by the law of cosines, figure it out. And then you should get a very weak field here on the edge because the magnetic field kind of curves around, you see, and then at the edges is very weak compared to anywhere in the center.